I am Bursa. I am a World Heritage Site from the depths of history. I am a depository of civilizations on the foothills of Mount Uludağ. I am the ancient capital of the Ottoman Empire and its enduring spirit. I am Bursa. I am the prayers and calligraphy of the Ulu Mosque. I am the tiles and ceramics that give the Green Mosque its name. I am the houses of worship in Iznik, once home to Romans, Byzantines, Seljuks, and Ottomans. I am the Muradiya Mosque complex, where life and death, dreams and reality, poignance and joy are contemplated. I am a boundless land of legends, the living cultural heritage of Cumali, the sun setting on Gölyaza Lake. I am nature's gift to humanity. I am the color green in all its shades. I, a centuries-old sycamore, tones of blue and green, sun and lake, am Bursa. I am the eternal beauty of the Longbows forest. I am the rushing waters of the Sai Tabat and Suuchtu Falls. I am a city of flavors, where history meets gastronomy. I am crispy jantik from a wood-fired oven. I am the finest olives and olive oil. I am the birthplace of Bursa kebab. I am köfte with pide and inegöl köfte, that is, a paradise of Turkish-style meatballs. I delight palates with sensational flavors, like soft tahini pide and candied chestnuts. I am a land of fresh fruit and nature's bounty. I am paragliding between sky and forest. I am the center for adrenaline and nature sports. I am the timeless shadow puppets, karagas and hajavat. I am handicrafts at Erganda Bridge, a steel knife forged in fire, a smooth silk shawl from Kozahan, a handcrafted Iznik tile. I am the last stop before Europe on the Silk Road, the covered bazaar. I am so much more than a city. I am Bursa.
Okay. Morning. It was such a good start. Okay. Good morning to everyone. I'm the chair of the session, Ozgur Ozdemir. So today we have 4 presentations. So I guess we're gonna have enough time. For each presentation, we will have about 15 minutes. And with the questions, discussion, we will have like 2-3 more minutes. So that would be enough for timing. So please be strict on that timing, okay? So our first presenter, if I may, Mustafa Uzuner. He is from Istanbul Technical University, and he's gonna present the paper entitled as a model-based hardware implementation of traffic regulator in Orange 664 and system. Please, you can start.
Okay, thank you. You can see the screen, right? Okay. So let me start. My name is Mustafa Uzuner. We presented a paper, and the presentation is about model-based hardware implementation of traffic regulator in RNG 664N system. So first, I will start with a simple introduction. I will talk about the deterministic networks RNG 664N system. about the properties. And then I will briefly mention about the single queue model that we built by using MATLAB Simulink. And then I will mention the MATLAB HDL coder, the tool that we use for hardware implementation. Then I will extend the single queue model and introduce you the ARINC 664 instance model. Then I will show you some simulation.
Mr. Uzuner, sorry to interrupt, but we are just seeing the first, at least
Really?
only the first presentation, the title one. And can you make it as a full screen, please? Because you already moved to the outline, but we are not seeing the outline slide.
Yes, okay, sorry, maybe.
Can you make the okay, yes, great, thank you.
Okay. I only share the rather than the entire screen. Share one slide. Okay, sorry. So as I told you, then I will mention about the ARINC and system models. Then I will show you some simulation implementation results, and then I will conclude this presentation. So deterministic networks are widely used in real-time applications. They aim to provide low data loss rates, low packet delay variation, in other words, jitter, and bounded latency. Some popular usage areas are automation technologies, also automotives, aircraft systems, and video streaming. And state-of-the-art D10 standards are time-triggered Ethernet, time-sensitive networks, and ARINC, which is the ARINC 664, which is the main focus on this presentation. Time-triggered Ethernet has multiple traffic flows, and it has a very complex time synchronization mechanism, and it has very strict timing rules. It's mainly used in aerospace and automotive industries. And also time-sensitive networking, also many traffic flows, and it has a IEEE 1588 time synchronization mechanism, and it's widely used in automation systems, automotive, again, and robotics. ARINC has a simpler way of communication with one traffic flow, one type of traffic, and there's no time synchronization. It provides end-to-end redundant communication by using nstems and switch. Well, ARINC 664, from now on, I will be referring as ARINC for simplicity, has three main components: nsystem, switch, and virtual links. Nstems exchange data frames from one source to another by using the concept of virtual links. Each message has a virtual link, and the messages are classified based on this information, their ID, virtual link ID. And also nSystem shape the traffic, shape the unregulated traffic. As you can see in the traffic shaping image, that unregulated flows are coming from a queue, but the nSystem regulates them by using the back parameter. Back parameter is special for each virtual link. So based on this value, the traffic is regulated. And also there is a switch between the two nSystems, and switch is responsible of filtering, policing, and forwarding Ethernet message to provide the deterministic network system. So first, I will talk about the single queue model that we built by using MATLAB Simulink, which is responsible of loading, storing, and serving Ethernet frames with varying rates and varying lengths. As you can see here, there are four modules, and loader, memory, and analysis modules are used for simulation. However, server module is used for simulation too, but also for hardware implementation. So in the loader module, the message generator trigger is responsible of triggering the system, determines when the message will be generated based on the rate and the length of the Ethernet frame. The message generator creates this message. Message loader loads this message to FIFO, to the memory. And then in the server module, the scheduler server block is responsible of serving the Ethernet frame from FIFO. And in the analysis module, we measure the jitter value for each Ethernet frames. So we built this model and by using a single queue, because we want to show that our model will be working properly. And then we validated our model by using queuing theory for some queues like MD1, DD1. And then before talking about the ARINC model, I would like to talk about MATLAB HDL coder that we use for hardware implementation. Building an RTL design with traditional methods consumes a lot of time, and a designer must also set up a verification environment from the early stages of the development, because it's one of the main properties. And as an alternative method, a model-based system by Simulink is very, very helpful, because Simulink has excessive libraries, multiple simulation libraries, and you can convert your Simulink model to HDL, to VHDL or Verilog by using the MATLAB HDL codon function. If you write the right code, and also MATLAB HDL coder and Simulink provides requirement tracker tools and design testing environment. So now I will talk about ARINC models. The ARINC and STEM model is the extension of single Q model. First, we validate that single Q model works properly, and then we extend this model. So in ARINC model, there are 4 components, again, 4 modules: loaders, memory, analysis, and server. However, loaders are based on the single Q model. Each loader is the loader of the single Q. So, and they run independent from each other for simulation purposes. And in the memory, each Q is stored in distinct VL, in FIFOs. And in the server models, there are 4 components. Shaper is responsible of applying the traffic shaping algorithm that I mentioned earlier. Eligible queues stores the queues whose back parameter is arrived, so which means the queues are eligible. Scheduler decider is responsible of deciding which queue to serve according to the scheduling algorithm, and scheduler server is responsible of serving the frame, Ethernet frame, based on the outcome of scheduler decider. And in the analysis module, we keep the statistics for each queue. So most challenging part of this simulation environment is the server model, because it also will be implemented in hardware. And in the server model, we tried 4 different algorithms. These algorithms are small spec, FIFO, smallest size, and longest queue algorithms. Small spec algorithm serves the VL with the smallest spec value among all eligible queues. FIFO algorithm serves the VL whose head of line arrival time is the earliest among all eligible queues. Again, smallest size serves the VL whose head of line is the smallest, and longest queue serves the queue which has the highest number of bytes. So here is an example implementation of the small spec algorithm. So we implemented all 4 algorithms, but here I show you the small spec because the others are very similar to that. So you see there's a Moore state machine in here, and our ARINC model's service rate is 1 gigabit per second. We decided to do that way, and the data width is 8 bits, so which means the clock frequency must be at least 125 megahertz. So what we do is here, first, we mask the back values. We mask the back values because if the queue is not eligible, then there is no need to use that queue. So if the queue is not eligible, the outcome of this mask module is the maximum possible integer value. And then we find the smallest back value among all queues. However, the clock frequency is very high. Therefore, it's not an applicable method to find the minimum value in one step. So at each step, we found the minimum value among 4 queues, and then our model in the simulation environment is based on 8 queues, which means that we found the minimum value in 2 steps. And when we found the minimum value, if the minimum value is the maximum possible integer value, which means that all of the queues are not eligible, which means all of them are masked. So we trigger the system again, and we run the exact same procedure once more until we find the minimum value. So after building the ARINC model with various scheduling algorithms, we decided to build a dynamic scheduling algorithm. Each scheduling algorithm has their advantages and disadvantages. Therefore, we decided to build the system that you see here, the model you see here. So here, 4 scheduling algorithm exists: small spec, FIFO, smallest size, and longest queue. And in runtime, the user can switch among the scheduling algorithms with a select pin. So, and we store these informations to decide for algorithms. Arrival time is used for FIFO, HO, head of line length is used for smallest size, queue length is used for longest queue, and bag is used for, which is also used for shaper. Bag is used for smallest bag algorithm. So we provide some simulation results. We provide a configuration scenario for 8 queues, and each of them is in the mode of Poisson exponential mode, and the lengths varies from 64 bytes to 512 bytes, and the bag values in microseconds varies from 25 microseconds to 200. And you see the maximum jitter results that we provided by using the analysis module. So here for four algorithms, smallest spec, 5-post, smallest size, and longest queue. In the smallest spec and smallest size algorithms show the exact same behavior in terms of maximum jitter, because the queue who has the smallest size also has the smallest spec, so they show the exact procedure. And FIFO, there is no specific behavior because the arrival time is random, exponential mode. And in the longest queue, you can see that in Q8 and Q7 has the lowest maximum results because they are served with more bytes and each serving time. And also we share implementation results. We converted our Simulink model of the server to VHDL by using MATLAB HDL coder. And while doing that, we use Kintex 7 FPGA, and our clock frequency is 125 megahertz. So you see here the implementation results, lookup tables, flip-flops, and memories for 8 queues system. So FIFO algorithm spends the most resource because the arrival time information is 64 bits, but longest queue algorithm spends more resource than smallest size algorithm because longest queue needs a 32-bit information. However, smallest size is a 16-bit information. And smallest spec spends the least resource because it does not need any external parameter. It's just used the back parameter that we defined earlier. And in the dynamic schedule algorithm, of course, spends the most resource because compared to other algorithms, it's a combination of all these four algorithms, so it spends the most resource. To conclude this paper, we show that each scheduling algorithm has their advantages and disadvantages. Also, we prove that the FPGA implementation of Ring and system can be done by using model-based, in contrary to traditional methods, which consumes a lot of time. So, and also it's very easy to keep the statistics. So it was helpful. Simulink was very helpful. And in the future work, we are considering about building a dynamic scheduling model with self-determining property based on the outcomes from the analysis model. So, which means that, as I told you, each scheduling algorithm has their advantages and disadvantages. So, based on the calculations, based on statistics, we want to switch the algorithm in runtime, but with a smart method. But now we use it to the user. So we leave it to the user. User can switch the algorithm in runtime. So thank you for listening. It's the end of my presentation. Any questions? You're welcome.
I'm really sorry. I missed the ending. My internet connection just interrupted. Sorry, but at least I finally reconnect. Thank you, Mustafa. Thank you, Mr. Ozdemir. I'm sorry. So we could move to the next presenter. I guess she will be Beyza, our next speaker from Istanbul Medeniyet University, Beyza, and she will give a speech on the reconfigurable intelligent surface empowered differential cause shift keying, very long name, assisted media-based modulation over Nakagami-m fading channels. Please, you may start.
Okay. Can you see?
Mhm.
Okay. Have a nice day, ladies and gentlemen. My name is Beyza and I am joining from Istanbul. I am doing a Master of Science in Electrical and Electronics Engineering at Istanbul Medeniyet University. And also I am working as a research assistant here. First of all, I would like to thank the ELACO committee for giving us this opportunity to present. Today, I will talk about a new communication system design that we have proposed. Our paper's title is Reconfigurable Intelligent Surface Empowered Differential Couch-Shifting Assisted Media-Based Modulation over Nakagami-m fading channels. The presentation will be as follows. Firstly, we will define the problem. Then I will explain the introduction part where we describe three basic systems that form the proposed system, so we can better understand the main system model. Then we will examine the main proposed system model. And finally, we will evaluate the computer simulations and come to the results. As known, increases in the number of mobile devices and data sizes cause mobile data traffic. Thus, inefficient and poor quality communication occurs. New generation communication system designs should be developed continuously in order to meet the needs and demands such as high data rates, more reliability, high energy and spectral efficiency required by the technology that has gained momentum recently. In this regard, we designed a new system called DCSK-MBM-RIS by combining the DCSK-MBM technique, which has just been introduced to the literature, and the RIS technique that has been very popular recently. Different precautionary methods have been developed for reliable communication. One of these methods is chaotic systems that perform secure and fast encryption. Chaos theory, also known as the butterfly effect, is a study of Edward Norton Lawrence. In these systems, information is represented by chaotic signals. These signals are not periodic. And one of the techniques using this system, DCSK, differential couch-shifting, has a low hardware complexity and performs perfectly for multi-bit fading channels. This figure has a DCSK transmitter and the receiver. In the DCSK technique, the communication consists of two phases. And the couch generator generates the reference array using Chebyshev functions like that. And in the first phase, the only reference symbol is transmitted. And in the second phase, the reference array is delayed and then formed with the modulated symbol B, so that the information signal is created and then it's transmitted. Another promising technology for high data rates wireless communication is media-based modulation. Media-based modulation transmits data by changing the far-field radiation pattern of reconfigurable antenna and provides significant improvements in both data rate and spectral efficiency by using RF mirrors in transmission antennas to carry additional information bits. The MBM uses a single array with RF mirrors equipped with pin diodes. The index of active channel state determined by MRF bits. Different channel models are created by controlling the on-off configuration of the RF mirrors by the information bits. Totally N-map states occurs, each with a different channel structure. On the other hand, the spectral efficiency in the MBM system increases linearly with the number of RF mirrors used. Introducing the concept of intelligent radio environments, the configurable intelligent surface is an artificial surface made of electromagnetic material. Unlike the current wireless communication designs, the most important property of RIS is that they provide a controllable radio environment. RIS controls the scattering, reflection, and refraction properties of the radio waves, dealing with the negative effects of wireless propagation. It reduces power consumption and improves spectral efficiency and coverage via software-controlled, also low-cost metasurface reflectors. Because unlike the other technologies, passively reconstructs incident signals and combines reflected signals at intended locations with appropriate phase shift design. Briefly, it focuses the incident radio waves at specific locations by beamforming, thus maximizing the signal-to-noise ratio. We can illustrate all these mentioned methods with the simple math on the left. The proposed system is fundamentally based on 3 different techniques and has great advantages with the different advantages brought by these 3 techniques. With this study, the performance of the conventional system was carried further by adding the RIS to the DCSK-MBM method over Nakagami-m fading channels. This system model consists of 2 main structures, transmitter and receiver structures. Let's see the illustration of the transmitter structure. Firstly, the chaos generator generates the chaotic reference array of beta length using the Chebyshev functions like that. The communication protocols consist of 2 phases, as I said before. In the first phase, the reference array will be transmitted, and it is delayed by the amount of beta to form the information symbol. Also, a memory modulator output is needed to generate the information symbol. So let's check out this process. Firstly, the B bit vector applied to the input of the system, its size mt multiply 1. Let the B vector is given like that. Here, this information vector B is split into 2 subvectors. For instance, phi chooses symbol from MQM modulation by modulator. For example, phi is 1 and 0, it denotes the 1 minus G in QM modulation. On the other hand, AMRF bits are responsible for selecting one map via RF mirror switch controller unit. Then the delayed array and phi are multiplied to create the information symbol. We obtain. In the first phase, the reference sequence is transmitted from the selected active map, and in the second phase, the information symbol is transmitted from the SAM map. Also, the frame structure of the transmitted symbol is as follows. Its length totally 2 beta, and SEJ can given this equation. Then the signal goes over the Nakagami-m fading channel, and we're using a RIS in channel. Let's examine the receiver structure. Here, this equals there are 2 Nakagami-m fading channel coefficients. The channel between the transmitter and the RIS is denoted by H, and the channel between RIS and the receiver denotes by G. And we can express as follows. With the help of RIS, with the channel phase, theta and phi information, the phi k is adjusted in this way. Therefore, it is maximized the SNR at the receiver. It is assumed that the channel status information is provided to the RIS via communication software. The received signal is written as over the all of n RIS reflecting elements. Then we see the baseband signals. After that, the transmitted symbol and the map index are estimated by using ML maximum likelihood detector as follows. Then, consequently, with the bit-back mapping technique, using the results in the indexes and the transmitted bit sequences reconstructed at the receiver as like that, and finally estimated B. In this section, the computer simulations results are presented and compared in the presence of Nakagami-m fading channels for DCSK-MBM RIS, DCSK-Q assemblies, and DCSK-SM RIS techniques for various M and N values. M denotes Nakagami-m channel coefficient, and N is number of the RIS elements. For example, in figure 1A, 2 bits to carried by RF mirrors and 2 bits to be carried with the modulated symbol. In figure 1B, there are 2 active antennas. We totally carried 4 bits. There are 2 bits are carried in the index, and 2 bits are carried along with the modulated symbol. Some way in the figure 1C, 2 bits transmitted. 2 bits transmitted index and 2 bits transmitted with modulated symbol. The important things in here, all analysis was performed when the Nakagami-m parameter is respectively m equal 1, 2, 3, and 5, and the number of risk cells is stable and equal 22. Considering figure 1, it can be easily seen that the performance deteriorates when the Nakagami-m parameter increases. Furthermore, when the results is examined, it's seen that the proposed DCSK MBM system will perform much better than the other techniques. We can see another simulations. Figure 2 shows performance comparisons of DCSK MBMs and the DCSK SMRs techniques for MT equal 6 bits, and the Nakagami-m parameter was chosen as M equal 3. If we examine carefully figure 2, when the risk element is 128, the DCSK MBM technique provides a performance gain about 5.25 dB compared to the DCSK SMRs technique. On the other hand, in cases where n equals 32 and 60, it provides about 1 dB gain at the same bit error rate value. And in figure 3, the bar performance comparisons of the DCSK MBMs and the DCSK QSMs techniques for MT equal 6 bits are made. If we examine it carefully again, when the risk cell number is n equal 64, its DCSK MBMs technique provides a gain of about 6.9 dB compared to the DCSK QSMRs when n risk elements equal to 32. DCSK MBMs technique provides about 5.33, and in the case of n equals 16, it provides about 5 dB gain compared to the DCSK QSMRs technique. Finally, if all the performance curves are considered together, it can be seen that the proposed DCSK MBMs technique obviously provides a remarkable performance against the other techniques mentioned, other SM techniques. In this study, a novel communication system called the DCSK-MBMs has been proposed, which has the potential to provide a perfect solution to needs and problems that may take place in new generation communication techniques. Bit error rate performance comparisons of the DCSK-MBMs system with the DCSK-QSMRs and the DCSK-SMRs techniques are also examined. According to the computer results, the proposed system has a better error performance compared to the other systems. After all, advantages of the DCSK-MBMs systems can be said: improved bit error rate performance, high reliability, high data rate, and high energy and spectral efficiency. Thank you for listening. Any questions?
Thank you for the presentation. Now we may questions. Anybody? Okay, I have a question. So you changed the number of elements in the IRS to check the performance of the system. So by changing this element number, are you just, the changing the element size, each pixel size, or you are just changing the whole IRS size? So you are keeping the element size constant or not?
Just number of risk elements, all of
Yes.
them, the accused size.
Okay. So you are just increasing the size of the whole IRS.
Yes, if we can increase the number of the risk elements, its size bigger than before. Yes.
And the change of this, the changing the size improve the performance?
Actually, maybe a power consumption a bit more high, but we gain the bit error, better bit error rate performance. Is a maybe trade-off a little.
Okay. Thank you. And can you tell me the size of it? Do you have it? What is the size of this, the IRS or the element size, physical size?
Especially I don't exactly know.
Okay. Thank you again. Thank you.
You're welcome.
If we don't have another question, so we move on to the next presenter, but Ahmet Ozcan is not here, so we are moving to the paper 99. Mr. Öner, Muhammed Yusuf Öner from Gazi University. He will present the paper entitled Transmission Performance Analysis of Cognitive Radio-Based Backscatter Communication System. Okay, thank you. You may start now.
Can you see my presentation?
Yes, we can.
All of you are welcome to my presentation. My name is Muhammed Yusuf. I'm a research assistant at Gazi University. I am also doing a PhD in communications. My advisor, Associate Professor Ozgur Ertuğ. In this work, I will tell you about our work on backscatter communication. Table of content, the aim of the work, an overview of backscatter communication technique, system model, numerical results and observations, conclusions and future work, and references. The aim of the work in this paper, optimal time allocation for the users in the cognitive radio-based backscatter communication networks, and the maximization problem of the total received data from these users analyzed. In this model, it's desired to transmit the data of the multiple users to the receiver by using TDMA, a time division multiple access technique. The system was modeled mathematically and turned into an optimization problem. Then backscattering transmission and energy harvesting times and will maximize the total amount of data sent from the users to the receiver are determined, and performance results are given in terms of the total data received by the receiver. Finally, the model was compared with the station where users only backscatter and only energy harvest and transmit mode, and the model analyzed showed better performance. An overview of backscatter communication technique. In the backscatter communication method, the users modulates the signal received from the power station and sends it to the receiver. The modulation process of the signal is adjusted using the reflection coefficient of the antenna. If the load impedance of the user's antenna is changed, the antenna reflection coefficient also changes. Change in the amplitude and phase of the reflection coefficient determine the modulation on the backscatter signal. For example, a change in the amplitude modulation, or a change in phase modulation. Here, modulation is mentioned in general. Other modulation techniques have also been made. The antenna reflection coefficient is calculated as given in equation. This antenna impedance ZA, load impedance ZE, figure B, front side of the backscatter user. Next slide. As shown in figure B, figure 1, the reflection coefficient is changed by switching between two loads, Z1 and Z2. In this change, two different stations arise, namely observation and reflection. In the case of impedance matching, the radio frequency signal is observed, and this is represented by bit 0. In the opposite impedance mismatch, the radio frequency signal is reflected towards the receiver. This is also represented by bit 1. This variation between two states is called loop modulation. Okay, the advantage of the backscatter communication method is that users do not need a battery to perform data communication. Backscattering takes place passively. The user does not need to consume power. Users in the network can use the signal sent by the power station allocated to them, as well as communicate using any signal in the environment. Using this current signal of the users communicating with each other in the environment is known as cognitive radio-based backscatter communication system in the literature 5. In the study 6, overlay network is considered, and it's assumed that the primary transmitter cuts off its broadcast in a certain period of time. In this paper, different from the overlay network model in given 6, the underlay network model is considered. In this model, since the primary transmitter continues to broadcast uninterrupted, users have to keep the signal power levels below a certain value during active data transmission in order to avoid interference in the primary receiver. Figure system model. In this paper, the system model shown in figure 2 is considered. The communication network consists of primary transmitter and secondary transmitters and secondary receiver, well, gateway. ST and SR constituting the secondary canal use the infrastructure of the primary transmitter constituting the primary canal and primary receiver, which is its own receiver. Users in the secondary canal can boot backscatter communication. In addition, after harvesting energy, it can perform active data transmission by using this energy. The time structure is shown in figure 3. Backscatter mode occupies 1 minus beta time in the communication time block. Users harvest energy during 1 minus phi n minus tau n and backscatter the signal at time phi n. This harvested energy is used in the tau n time interval during which each actively transmits data in energy harvest and transmit mode. Backscatter time and active data transmission time should satisfy the following expression as seen in equation 1 and 2. The total backscatter time of n cannot exceed the 1 minus beta. In addition, since the times given in time block cannot be negative, it can be written as phi n tau n is greater than or equal to 0. Our aim is to maximize the total amount of data reaching the receiver by finding the optimal backscatter time, energy harvesting time, and active data transmission time. The total data transmitted to the secondary receiver by the secondary transmitter is given below as seen in equation 3. Our sum, where RMB, the number of bits transmitted by users in backscatter mode, RNH, the bits transmitted by the user in harvest and transmitting mode. Backscatter mode, the data sent by STN in backscatter mode is found by the equation phi n times b, and b is equal to Rn. B is the user's backscatter rate, which can be adjusted by an RC circuit consisting of resistance and capacitance. Energy harvesting transmitting mode, first in energy harvest and transmit mode, the power stored by each user is found by the Friis equation as follows, where the transmit power of the primary transmitter is P8 PT, energy harvesting efficient is sigma n, and PT antenna gain is GT, the GT. The STN antenna gain is the GNR. The wavelength of the signal is lambda. The distance between primary transmitter and secondary transmitter is dn. The harvested energy by each user is given as follows as seen in equation 5. Secondly, the harvest energy is used in active data transmission. The transmit power of the STN user during the allocated to n period is given by the following equation. While the primary transmitter is sending a signal to its own receiver, the primary receiver, backscattered by the STS towards this secondary receiver does not cause serious interference in the primary receiver due to the low power level of the backscatter signal. However, active data transmission can cause a distorted effect on the signal received by the primary receiver. To prevent this, secondary transmitters have to transmit data under a certain power. To ensure this, the power constraint is written as PN primary transmit power is less than or equal to P plus. This equation P plus is the predetermined reference power value. The transmit power of the users cannot exceed this value to avoid interference in primary receiver. As a result, the active data transmission rate of the secondary transmitter STN user can be expressed by the following formula. This formula is channel capacity. Here, the transmission efficient is Kn, the bandwidth primary canal. Pn0 is defined as the ratio of the noise power N0 to the canal gain coefficient H0. The number of the bits transmitted by a user to the secondary receiver in energy harvest and transmit mode is given below, as seen in equation 8. The total number of bits transmitted for both backscatter mode and energy transmit and energy harvest mode expressed in the following equation, our sum. In addition, each user is expected to satisfy the quality of service. For this, the number of data sent by the user must be equal to or greater than predetermined value. Thus, Rn or greater than or equal to Rn plus constraint can be written. As a result, the system is an optimization problem and is given by the following equation. Rn to maximize our sum over phi and tau for constraint, subjective for constraint. It can be easily found that the objective function of the above problem is concave. The problem can be solved by using optimization methods. Okay, next slide. The numerical result of observations. For the simulation result, the CVX toolbox in MATLAB, the performance of system model is compared with the network models operating in backscatter mode only and energy harvest and transmitting mode only. A figure shows that when the frequency of the signal emitted by the primary transmitter increases, the power harvested by users decreases. As can be clearly seen in equation 4, the power stored by the users decreases with the square of the frequency. Next slide, figure 5. Figure 5 shows the total amount of data reaching the receiver according to the number of users in the secondary canal. The backscatter rate of all users in taken is 24 kilobits per second. As the number of secondary transmitter users increases, the total harvest energy reaches high values. Therefore, the system performance has improved. In addition, as long as the number of users increases, the active data transmission time allocated to each user becomes shorter and the transmitted power increases from the formula in equation 6. In order to prevent interference in primary receiver, it's important to keep the power levels below a certain value. In this article, higher data transmission rates were obtained than in the study literature 6. Because secondary transmitters harvest more energy and use this harvested energy in active data transmission. In addition, since the primary canal is not muted during beta, secondary transmitters backscatter signal in the time allotted to them during the entire time block when operating only in backscatter mode. Only in the backscatter mode, the total data transmission rate does not change according to the number of users. Okay, next slide. Figure 6. Figure 6, in figure 6, the backscatter rate one of the second transmitter users is considered as 24 kilobits per second and the others as 40 kilobits per second. The user with a low backscatter rate was given a short time to scatter. As a result, more energy was harvested in the backscatter mode. In order to use this harvested energy efficiently, a longer active data transmission time is reserved for the user with a low backscatter rate. When we look at figure 5 and figure 6 carefully, the total data transmission rate does not change depending on the backscatter rate when the users only work in the energy harvest and transmitting mode. As a result, users' backscatter rate does not affect system performance in this mode. However, the increase in the number of the users increases the total energy stored by the users in the network, thus contributing positively to the system performance. When operating only in energy harvest and transmitting mode, the amount of data sent by each user to the receiver is found from the expression in equation 8. This expression is an increasing function with respect to tau n. Although the total number of bits transmitted increases as the number of users increases, the active data transmission time allocated to each user becomes shorter and the amount of data sent by each user decreases. Therefore, the Rn is greater than or equal to Rn plus constraint is not met and service quality may decrease. Okay, next slide. Conclusion and future work. In this paper, optimal time allocation for the users in the cognitive radio-based backscatter communication networks and the maximization problem of the total received data from this user is analyzed. In the network, different from overlay network model in given 6, the underlay network model is considered. In this model, since the primary transmitter continues to broadcast uninterrupted, users have to keep the signal power levels below a certain value during active data transmission in order to avoid interference in the primary receiver. With this approach, the system was modeled mathematically and turned into an optimization problem. Then, the most appropriate backscattering, the transmission and energy harvesting time were found by simulation, and the total amount of the data reaching the receiver was maximized. Compared to system in 6, it was seen that better result for obtained in terms of data rates. For the future work, we will evaluate the system was MIMO, multiple input and multiple output, and examine its performance analysis. I end my presentation with your permission. Thank you for listening.
Okay, thank you for the presentation. We may accept the question now. Anybody wants to ask or make any comment? Then I have one question. So you were mentioning about the antenna impedance at the beginning. So what type of the antenna you were using in your simulations?
1 minute. This slide, antenna.
Are you using any specific antenna, or you were just using the concept?
No specific, general antenna. No specific antenna, general antenna.
Okay, so okay, thank you. So that might be the case. You may just, see the effect of the antenna type on your analysis. Maybe it has some effect too on energy harvesting.
Okay, thank you.
Welcome. So if you don't have another question, okay, we may move on. Actually, we may move on to the next presenter, but I guess he will have some explanation, not presented. Mr. Yalcin.
Okay, thank you very much. I'm very sorry to all the attendants. My students was planning to present this paper, But yesterday evening he had one health problem, and he's now in the hospital. Therefore, he couldn't present the work. And also, I didn't know that these things will happen, and I don't have any preparation to present. But basically, I would like to show you what was the purpose, and I would like to just explain the general idea on the paper. So sorry to everyone, I'm not well prepared. I just want to simultaneously explain the idea behind the work. If you have another further question, you're always welcome to send us to me personally all your question. I will try to explain, also to having the help from my students. If it is possible, I would like to share the paper. As I told you, I don't have a presentation, therefore I will try to my best to explain on the paper itself. So please use this email if you have any question about the paper, and we will try our best to reply you immediately. So the purpose here is in fact to testing the Ethernet performance. So this work has been done contribution with the students from the Assoc and academia, and there is the question is how we can test our device if it has a one Ethernet connection. So this is important because of the nowadays all these IoT devices has some Ethernet interface, and also in many application, Ethernet is the basic part in the embedded system. So for the interfacing the information gathering from the environment. So the question is how fast our Ethernet interface is working. If there is a one mistake during the design, we should understand that behavior. So basically what we have done to testing the one devices. This is the most important picture in the paper. So this is the Ethernet test system. The test model is designed during this thesis, and we are using a FPGA zinc type FPGA. So it including the two core ARM core. So the purpose use one of the core for the generating the pattern, and the other one, in fact, to analyze the package information. So here in this picture, you see that our test model design in this the work, and we have one green module unit under the test. So the purpose is the testing the interface between our test module and the test computer. Okay, so we will exchange the information between this UUT and our test module, and measuring the performance of how fast we are sending the information to test computer. And as you see here, you have a control computer. This is connect to our test module via the USB, and it has a hyperterminal. This hyperterminal, in fact, using this hyperterminal, in fact, we can program our test model. We can ask our test model to generate a different pattern, and also to gathering all the data, all the test result from our test module. And then the idea here to, of course, to design this system, and in this test module, so if you look in the literature, you can find many test models. They are designed for specific application, and also if you look the price of this test model, it's quite expensive, and they have many industrial application. Test model has more facility than what you need, and therefore it's normal to have them to be expensive. But what we wish to have it a more practical one, and then also from the engineering point of view to have a cheaper one. And also the purpose here was to have some user-friendly interface using this control computer, and designer just want to design to organize or to program their test bench, and load to this course, one of the course, and then the course generate all the pattern and gathering all the transmitted and received information, and then report you. And in this system, full of them is designed in the FPGA, and this is the figure 2 is in fact show all the module of the Ethernet test system. And in this test we also use different size of the Ethernet cable, and also that might be cases because in sometimes all these devices this test computer, just imagine that these are the one IoT devices far away from the center. Therefore, there might be a long Ethernet cable, and also it could be a shorter and a longer, and we have to see that the performance of the data communication depend on the length of the cable. So here we have plenty of the test. Thanks to the programmability property, we sent many packages and to measure the transmissions times. Table 3 is in fact to show the transmission times and also to show the latency between the module. So in fact, so this is the work. In fact, the purpose was to have a practical equipment to use it also in the industrial environment. So in many test equipment is not practical to carry from in the industry also in the area of in the field. So because all these IoT devices in the field, and you just want to have a small size of equipment to measure all this performance, because after you need the IoT devices, you want to be sure that there will be no problem for the transmissions of the data. So that are in fact all I can say. If you have any further question, please email us or please personally you can send to me, and I will try to my best to give you more information about the work. Also, we can share you with our paper for the further help. That is all my thing will say about the paper. Please accept my apology for these things happened.
Thank you. Thank you. It was, I guess it was such a nice and covered presentation in such a short notice. Thank you again. And do you have, somebody have questions to Professor Yalcin? Okay, no. Okay, thank you again.
Thank you.
I guess thank you all the presenters and the attendants. So we may end the session now. Thank you.